But today I would like to talk about a really important element of and the magnetic field produced by this particular element. I'm talking about an element which is referred to as a solenoid, and solenoid is also, has a relatively high symmetry, so it is easier to derive an expression for magnetic field produced by a solenoid from Ampere-Maxwell equation than Biot-Savart law. We can also make some. We will make some conclusions from Biot-Savart law as well. Solenoid is made by coiling a piece of wire, and then when we run current through it, then this is a solenoid. So really, solenoid is a coil of wire through which, but however, it is designed to work as an electrical element. So if we run wire through it, it produces magnetic field. And actually, we can now think about what kind of magnetic field. Where is it really strong? Where it is weak? And what type of magnetic field we have there? Well, outside, actually, if you take a look at the magnetic field lines outside of the solenoid, these are the magnetic field lines produced by the solenoid. So inside the magnetic field, if you run current this way, magnetic field will be to the left. And how about if we actually try to determine it using right-hand rule, because right-hand rule should say what should be the direction of magnetic field. So how about if I think about, let's say, a fragment of the wire at this point? So which way the current flows? Consistently with this drawing, is it into the screen or out of the screen? Into the screen, right? Now, let's say that we use this simplified version of right-hand rule, in which we align the thumb with the direction of the current. So I will have to align direct my thumb into the screen, and then those four fingers show that below the wire, magnetic field is toward me. Above, it is in the other direction. Right, so indeed, we can conclude that on this side we have magnetic field to the right. On this side we have magnetic field to the left. We could use right-hand rule consistently with Biot-Savart law. So again, for the same segment, product of the segment vector would be in, right? So the segment. The segment vector is in. Now, position of the point of interest is down with respect to the segment. And so I align first my hand with the direction of the segment vector. Now I have to be able to bend my fingers in the direction of the unit vector toward the point of interest. And the thumb shows the magnetic field. So no matter how you use right-hand rule, you will conclude that inside of the solenoid, magnetic field will be to the left, and outside it is going to be to the right. Now, if I think about, if I place a bar magnet here, it would also produce produce a magnetic field like these. And inside, actually, it would also produce, although we cannot put anything inside of that magnet. So consistently with bar magnet, this side of the solenoid would correspond to the north magnetic pole, and this side of the solenoid would correspond to south magnetic pole. But rather than thinking in terms of poles, I prefer that you think in terms of magnetic field vector always. I consider that poles just confuse us. Anyway, let's now try to evaluate how strong magnetic field is and where. Well, so if I start from the outside over here, or let's say that solenoid has length L and it has N loops. Outside of the solenoid, magnetic field is approximately 0. And now, how can we see it? Well, consider contribution to magnetic field. I'm using almost Biot-Savart law. Well, precisely, Biot-Savart law. Consider contribution from this side and from this side. Here, current flows in. Here, current flows out. So let's consider this one. We figured out that this side produces magnetic field in this direction. However, if I take a look at this segment, current flows out, so contribution to magnetic field from the bottom side is to the left, is opposite. And actually whenever I consider a segment on one side and on the other side, I will see that magnetic fields tend to cancel each other. They don't cancel completely, so this is why we have approximately. Magnetic field here still exists because in Biot-Savart law we have also dependence on the distance from the segment. So if I consider a certain point over here, let's say that this segment is closer than that one, which means that magnetic field to the right is stronger than magnetic field to the left. So despite they cancel each other, they don't cancel each other completely. So it is approximately 0. However, inside, if we consider now magnetic field inside, look that the contribution from the top segment is to our left, and contribution from the bottom segment is also to our left. And if you consider all segments, you will see that they all add magnetic field in the same direction, to the left. So magnetic field inside is much stronger than magnetic field outside. And the magnetic field inside of the solenoid is equal to the permeability of free space. N stands for number of loops per unit length, and I is the current flowing in the solenoid. And actually we can easily derive this formula looking at the Ampere-Maxwell equation. Because imagine now an Amperian loop of a shape like this. So the left-hand side of that equation, which is the line integral of magnetic field, will be relatively easy to calculate, considering that assuming that outside magnetic field is 0. Let's see if I can do it on the whiteboard, because I'm not sure if I. All right, so if we want to evaluate this line integral, I can recognize, well, one thing is that if this solenoid is much longer than wider, I can consider that this is a very long solenoid, infinitely long. Then I can conclude that magnetic field along the line everywhere has the same value. I mean, the straight line passing through that inside of the solenoid. So magnetic field strength has the same value. So I can take out this strength in front of the integral, and then I have to integrate, well, magnitude of vector ds is equal to the length of the segment, as I will have now integral of, let's put it in, of ds and cosine of the angle between the segment, which I pick to the left, and magnetic field is to the left, so cosine of 0. So this is the value of the integral, line integral inside of the solenoid. Now, outside of the solenoid, we already concluded that magnetic field has a 0 value, which means that the entire integral outside is going to be 0. And if I integrate that, I will have magnetic field strength multiplied by the length of the solenoid. So this is the left-hand side of Ampere-Maxwell equation. Now, the right-hand side of Ampere-Maxwell equation says that I have now to consider the total current flowing through the surface spanned by that loop. And that current includes both, in principle, both conduction current and displacement current. Well, over here we have only conduction current. I took this loop, and so what is the current flowing through the surface spanned by that surface? Well, current crosses the surface at these points. So it will be the number of loops which I had multiplied by the current flowing in a single loop, and I have to multiply it by permeability of free space. That is permeability of free space times number of loops multiplied by the current. So from here I can conclude that magnetic field strength is permeability of free space, number of loops per unit length multiplied by the current. All right. And how about, why don't we play a little bit now with the, I brought here a demonstration which will, well, actually for quite a lot of things. I'm going to show you magnetic interaction, and also that a solenoid produces magnetic field. I have here a device which is called the cathode ray tube. Over here we have an electron gun. Actually, this part. This is up to this point. Here is electron gun, which we discussed in the past, and this electron gun shoots electrons toward that screen, and when the electrons hit the screen glows. So at the spot where it glows, it means that electric beam falls over there. Right now, actually, well, it is not good actually to shoot at the screen with electrons at one point, because this way you make holes in the screen, in the sense that the substance, that phosphor, which glows, is removed from the glass, and the spot doesn't stops glowing. Although I could stop this beam, so momentarily I will do that. Yeah, I can hold it in a particular location. Now, this cathode ray tube is actually designed in such a way that that from the left to the right, the beam is directed by two parallel plates and electric field. So electric field deflects it to the left and to the right. However, if I take a magnet, I can play with that too. Where do I? Here is the magnet. As I took the same magnet which we played with yesterday, and I'll stop the beam, and now I bring the magnet over here. And actually, I want you to see how that beam is deflected. All right. I mean, this is good. Yes, so for example, right now, I'm bringing south pole is here, north pole is here, which means that I'm bringing magnetic field in which direction? What is the direction of magnetic field at the location of the beam? Well, bar magnet, I mean, we saw magnetic field lines yesterday. It produces magnetic field lines from north pole toward the south pole, right? So magnetic field below the magnet, below the south pole, is toward the magnet. It's up. And so I was putting electrons traveling toward the screen in magnetic field up. All right, let's figure out what should be the deflection of the beam. Yes, so velocity of the particles was in this direction, of electrons. Magnetic field was up. Product of velocity and magnetic field would be to your left, and I have to multiply by negative charge of electrons, which means that the force is going to be to the right, which actually should make us happy, right? I mean, this is what we observe. When I bring south pole toward the beam is deflected to your right. So what will happen if I bring the north pole? Well, if I bring north pole from the top, or how about, let's start from the bottom. What will happen if I bring the north pole from the bottom? Which way the beam would be deflected? Also the same direction. Try it. And indeed, we see that, right? The closer I bring the beam, the magnet, the stronger the beam is deflected to your right. Now, how about if I bring the beam from the north pole from the top? Right. So now the magnetic force is supposed to be in the opposite direction. And we see that this also happens. What will happen if I bring it from the side? It's up, right? And from this side, it's down. All right. Okay, now here I have three solenoids. And I will connect. I'll connect just one. So this one will produce magnetic field. And all right. So right now, potential voltage which I apply to this solenoid is 0. So current doesn't flow in the solenoid. Now I increase potential difference, and well, we see that the beam was deflected. Let me stop it, right? So it is deflected down. Is it correct prediction? Well, what is the direction of magnetic field produced by the solenoid? It's horizontal, right? So magnetic field is horizontal. Why don't we actually figure out which way the current flows here? Let's say that it's a solenoid wound exactly like that one. If it were wound like this. So which way the current would have to flow? Because if I increase the current, the beam is deflected down. I will keep it like that. How about here? So magnetic, it means that magnetic force on the electrons were down, which means that product of velocity of electrons and magnetic field was up, right? Which means that magnetic field had to be which way? If velocity is this way, I already showed it. Yeah, so I concluded immediately that magnetic field produced by this solenoid has to be this way. Because now product of velocity and magnetic field vector is up. If you multiply by negative charge of electron, the force on electron is down. So magnetic field produced by this solenoid is, at this moment, is in this direction, which means that the current has to flow this way. Right now, current in the solenoid must to flow this way, consistently with this drawing. Yeah, because now, if I consider that segment on the top, I align my thumb with the current, and the fingers show the direction of magnetic field. You see that? That's all of this is how the segments on the solenoid contribute to the magnetic field. All right. How about if I put, if I take it from here and put it there? Let's make it the other way. Yeah, so now we see that this magnetic field produces, deflects the beam to your right. Okay. Now I would like to talk about this, what happens if we place various substances into magnetic field. It's kind of similar like with electric field. If we put substance into the field is affected. I mean the field which is produced by something else. So I can think that, for example, this is B0 is magnetic field vector of the magnetic field produced by a solenoid, and we put a certain substance in the solenoid. Now the molecules of that substance will align themselves in a particular way and produce its own magnetic field. So now we have within the substance magnetic field, and actually in vicinity as well, the field is a superposition of the field produced by the solenoid, or this external field, and the field produced by the substance. I'll call this new field, this field produced by that matter, Bm. So now magnetic field produced by the entire system consists of magnetic field produced by an external source and magnetic field produced by the substance. Now the magnetic field produced by the substance is proportional to the external magnetic field. This proportionality coefficient is represented by a Greek letter chi, this proportionality coefficient is called magnetic susceptibility of the substance. Depending on this, what is the value of magnetic susceptibility, we classify substances into paramagnetics. Paramagnetics are substances for which magnetic susceptibility is actually should be positive, greater than 0. Paramagnetics produce magnetic field in the same direction as the external magnetic field. Diamagnetics produce magnetic fields in the direction opposite to the direction of the external field. And from the application point of view, this group is very important, referred to as ferromagnetics. And ferromagnetics are substances, these are really paramagnetics with magnetic susceptibility much, much greater than 0. So they produce magnetic field in the same direction as the external magnetic field, but much stronger than that external magnetic field. It could be 100 times, magnetic field produced by the substance could be 100 times stronger than magnetic field produced by that external source. Ferromagnetics exhibit one more interesting feature. If I plot magnetic field produced by the substance versus magnetic field in which that substance is placed, I will get a curve which is referred to as hysteresis of magnetization, and it looks like that. I mean, let's say that I started with a substance which has a zero internal magnetic field, and place it in the external field. Well, as I increase external field, internal field is going to grow as well, up to a certain point. At this point, increasing magnetic field will not change. External magnetic field will not affect the internal magnetic field, which actually is kind of. I mean, one can imagine. You can imagine that all molecules are aligned already in the with that external magnetic field, so you cannot align something which is completely aligned more, right? However, if I start removing this external magnetic field, the internal magnetic field will not decrease along the same line. It is going to increase along a different line. Actually, it is going to I mean, what will happen is that even when the external magnetic field drops to zero, internal magnetic field still exists, which means that this piece of the substance still produces magnetic field. Do you see an application of it? Well, here it is. This is a piece of a ferromagnetic substance. Only ferromagnetics have actually this property that you can remove external magnetic field and it will still produce magnetic field, well, due to alignment of molecules in this piece. All permanent magnets are made from ferromagnetic substances. We can have magnetic field produced by this substance without putting this substance into external magnetic field of a solenoid, for example. In order actually to demagnetize this, we would have to put external place that substance in an external magnetic field opposite or opposing the internal magnetic field. So eventually we could destroy the magnetic field of this substance. And if we continue actually decreasing this magnetic field, we can reverse the orientation of the magnetic field produced by that substance. This curve is called hysteresis of magnetization, and hysteresis of magnetization is necessary to create or to make permanent magnets. So the internal magnetic field exists even after the external field is removed. All right. Now I would like to come back to Faraday's law of induction. Faraday's law of induction, well, and apply it, and actually apply it. In Faraday's law of induction, as third Maxwell's equation, I mean, the loop was just an arbitrary line. But think now what will happen instead of having an arbitrary, well, abstract line, we place a conductor. So now I'm going to put a ring over here, or maybe even a coil, a lot of rings. If the flux, magnetic flux through this surface varies, then that electric field will result in electromotive force in that loop. This phenomenon is called magnetic induction. And in fact that an induced electromotive force appears in a conductive loop when we change magnetic flux through the surface spanned through that by this loop. This is called magnetic induction. Now the value of this electromotive force is well, if we had just one loop, then the value of electromotive force would be equal just the would be just opposite to the rate of change in magnetic flux. Now this opposite also relates the directions of electromotive force and magnetic flux. However, it also relates it by right-hand rule. So if I consider, for example, if I consider magnetic flux toward us, then I would have to consider electromotive force in the counterclockwise direction, following the right-hand rule. Actually, for one loop, I can recognize here because really, what is electromotive force? Electromotive force was how much work was done on charged particles as they move from one location, from one side of a source to the other side of the source. So it was a really line integral of electric field vector. And Faraday's law of induction, I mean the third Ampere Maxwell equation, the third Maxwell equation really has line integral of the electric field on the left-hand side. So I can recognize that this line integral, if I put a loop over there, will be the electromotive force. And well, if we have several loops, we can think about it like having sources connected in series, like connecting batteries in series. If I take 1.5 volt battery and connect it to another 1.5 volt battery in series, what will be combined electromotive force? It will be 3 volts if they are connected in series. So here we have each loop is connected in series. Each loop produces magnetic field proportional to the, opposite to the rate of change in magnetic flux. If we have n of them, then electromotive force will be n times greater. Well, in principle, Faraday's law of induction would allow us immediately to determine what will be the direction of electromotive force depending if the flux is increasing or decreasing. It would be exactly the same way as we did as we analyzed electric field vector when we were imagining bringing magnet in and magnet out, so changing magnetic flux. But one can also determine it by using Lenz's law. Lenz's law, actually, according to me, doesn't even deserve to be called law. It should be rather a rule. But since it is in the book, it is referred to as a law, then let's stick with the law. It says that the polarity of electromotive force is such that it tends to produce a current opposing the changes in the magnetic flux. So, for example, let's think about it. What will happen? Yeah, we remember. I mean, you could remember that if we were moving magnet away, that electric field was counterclockwise along a loop. So if it is now a conductive ring, electromotive force will be counterclockwise. So it means that it will be trying to push current also counterclockwise. Let's see if it is consistent with the Lenz's law. All right. So if we move away magnet, what is happening with the flux? It is decreasing. Flux is decreasing. Lenz's law says now that the electromotive force will try to prevent the decrease, which means that the current which is induced in this loop will try to create magnetic field in the same direction, to reinforce that weakening magnetic flux. So which way the current has to flow in this ring in order to prevent decrease of the flux? Well, the current in the ring will attempt to produce magnetic field in the same direction, right? In order to prevent the decrease of the flux. Well, it means, let's consider this side. Yes, some magnetic field is in this direction. So if I use right-hand rule, I can figure out that the current has to, on the top segment, in the top segment, has to flow to your left. Over here, it has to flow this way. Now, over here, it has to flow this way. So current over here has to flow this way. So if we move the magnet away, induced current would indeed flow counterclockwise. Now let's see how to use Lenz's law if we bring the magnet toward that loop. And so if I bring it toward the loop, magnetic flux is growing. Therefore, induced electromotive force will tend to produce current which will prevent growth of the flux, which means that the electromotive force, that current will try to produce magnetic field into the board, into the screen, in the opposite direction, to prevent the growth of the flux, which means that the current would have to flow clockwise. Yeah, so if I consider this segment, current flowing this way, these fingers show that the magnetic field should be in. Let's consider this segment over here. Current flowing up will produce magnetic field in. Well, let's now take a look at some applications of magnetic field produced by solenoids and induction. Let's think that we arrange two coils in such a way that they share magnetic flux. And we can do it by placing a piece of a ferromagnetic substance. So now that ferromagnetic substance actually keeps its magnetic field practically inside. It's just for practical purposes, because in engineering nothing is ideal. So we are talking over here about an ideal transformer which doesn't have any losses of energy. A real transformer has losses because some of because the fluxes are not precisely equal. All right, so let's say now that I connect a light bulb to one of those solenoids and connect a source of alternating current to the first one. In this configuration, the light bulb is going to glow, although there is no electrical connection between the light bulb and the source. Well, let's see why it doesn't happen. So let's try to determine electromotive force induced in this in the second solenoid. I could, if impedance of this element of the light bulb is sufficiently high, I can consider that this electromotive force is really potential difference produced by the right-hand side coil. And this electromotive force, according to that Faraday law which we just saw, is proportional to the number of loops in this coil and the rate at which the flux through the cross-sectional surface of the coil varies. This minus sign relates the directions by right-hand rule, however. Now, this magnetic field is produced by the first coil in an ideal transformer, this magnetic flux is going to be equal to magnetic flux through a solenoid, through a cross-sectional surface of the first solenoid. So I will use that formula for magnetic field in the solenoid and calculate the flux and calculate that flux. So the flux through the first solenoid is going to be equal area, cross-sectional area of the solenoid, permeability of free space times number of loops per unit length, or you can say number of loops in the solenoid divided by the length of the solenoid, multiplied by current in the first solenoid, and since I have substance inside, I have to multiply by magnetic susceptibility plus 1, magnetic susceptibility of this substance over here plus 1, which we just saw what happens in the in case of placing substance into magnetic field. Now let's differentiate. First of all, let's see what is variable and what is not. So how about A? Who thinks that it's a constant and we can take it in front of the derivative? You are correct. Permeability of free space. Good. Magnetic susceptibility of the substance plus 1. We can take it out. Number of loops in the first solenoid divided by the length. Yes. Current in the first solenoid. No, right? It's an alternating current, so this is time dependent. This is the only time dependent factor. I can take out all the factors in front of the derivative. And for a given transformer, this is a certain constant. I can call it constant M. And M stands for mutual inductance. So the conclusion actually is that the electromotive force induced in the second coil is proportional to the rate of change in the current in the first coil. Let me give you a puzzle, and this will be, I think, the last thing which I want to talk about today. What is the unit of mutual inductance? Amperes? No. Henries. Correct. Yeah, recall that inductance, which actually is, I mean, tomorrow we'll talk about inductance. Tomorrow we will talk about this, not tomorrow, Monday, how to make an inductor. And indeed, well, because this, here we have a quantity which is measured in volts. Here is amperes per second. It's exactly like in the definition of inductance. Mutual inductance and inductance, they are both measured in Henries. All right, so this will be all for today.